Finally, in part 2D, we will compute the last network measure of interest to us, the path length, which remember is the number of edges traveled from one node to another. And again, to compute the path length, we will download this function from the web. I'll go to that same website. The URL is here at line 186. And we'll download the function distance_bin. And if I scroll down through this page, I'm looking for that function distance_bin. It's under paths and distances. Here it is, distance_bin. It's for binary networks undirected, which is appropriate for our purposes. And so you can download that function. I've already done it and put it in your working directory. So let's do that. And now if you're interested, you can always have a look at this function and see how it performs. We can trust it in this case because it's been developed by our colleagues, Olaf Sporns in particular, who's an expert in these types of measures. And what it takes is a single input, our adjacency matrix, and returns the distance traveled between each pair of nodes. Now luckily, again, it's easy to use, so we can compute the distance for our binary net, our adjacency matrix A. We'll call this function, and let's see what happens. Now it takes a little bit of time, but eventually it returns the variable dist. So it returns this result. I can see in my workspace, we can ask what is the size of dist. It's 5 by 5. And so what does this represent? Well, let's look at it. So we can print dist at the command line. And what this is indicating is the path length from each node to every other node. And so if we have our 5 nodes, 1, 2, 3, 4, 5, which corresponds to rows, and our 5 nodes, 1, 2, 3, 4, 5, which corresponds to columns, we can read the distance from node 1 to node 1. That's the first entry. It has a distance of 0. I'll pull up our picture here, and we see, of course, the distance from one node to itself is always 0. The distance from node 1 to node 2 is 1. From node 2 to node 3 is 1, and so on. We can also look at the distance from node 2 to all of the other nodes. That corresponds to the second row. We see the distance from 2 to 1 is 1. The distance to itself is 0. And the distance to the other nodes is 2. So to get from node 2 to node 3, we follow 2 steps. From node 2 to node 4, we follow 2 steps. And from node 2 to node 5, we follow 2 steps. And the same is true for all the other nodes. So you can look at this distance matrix and see the distance between each node and every other node. So it's the path length between all pairs of nodes. Notice that it again is symmetric. The distance from 1 to 2 is the same as the distance from 2 to 1. So we have this symmetric matrix. We can flip it about the diagonal. Now we'd like to compute the average path length between all pairs of nodes. To do that, we can execute line 211, where we're going to sum up this distance and divide by 2. That accounts for our double counting. Remember, this matrix is symmetric. We're using this tricky command here. This allows us to sum up the distance over all indices, so we don't have to specify whether we're computing the sum over rows and columns. So you can read about that notation here. Essentially, it's just taking this two-dimensional vector and making it a one-dimensional object. So we're going to sum up over all distances, and we get the average path length. And again, we're dividing by 2 to take care of this redundancy, where we're counting the distance, in this case, from 1 to 2 and 2 to 1. So we divide by 2 to take care of our double counting. And we said we wanted to scale this by the number of possible node pairs. And we wrote down an equation for the number of possible node pairs in class. If we look at line 216, it's the number of nodes times the number of nodes minus 1 divided by 2. So n choose 2. In our case, n is 5, so we can compute this average path length measure in line 221 and 222. We're here, we're specifying the number of nodes, using this distance measure, summing up all of those values, and then scaling by the number of node pairs. And what we find in this case, the average path length has a value of 1.6, consistent with what we found in class and also consistent with our expectations. We expect the path to be somewhere between 1 and 2 steps, and that's exactly what we find.